In Part D of Section 2, we're going to interpret computer output and something called regression to the mean. All right, when Mentos are dropped into a newly opened bottle of Diet Coke, carbon dioxide is released from the Diet Coke very rapidly, causing the Diet Coke to be expelled from the bottle. So will more Diet Coke be expelled when there's a larger number of Mentos? Two stat students, Brittany and Allie, decided to find out. Using 16-ounce bottles of Diet Coke, they dropped 2, 3, 4, or 5 Mentos into a randomly selected bottle, waited for the fizzing to die down, and then measured the amount of cups remaining in the bottle. When they subtracted this measurement from the original amount in the bottle to calculate the amount of Diet Coke expelled in cups. So output from the regression analysis is shown. So it gives you a lot of information. Here's the scatter plot. Here's the Mentos versus the amount expelled. Here is the output from the computer that I'm going to show you how to read this. And then it also gives you the residual plot. So what's the equation of the least square regression line? And define the variables. So you're going to look at the output here. Now, what you're going to focus on here is what it says constant. That's the y-intercept of your line. Okay, and then underneath it, in this case, it has Mentos in it, so that is your slope. That's how many Mentos go in it. Sometimes it will just say variable or something different right here, but constant is always the top line, and the next line is always your slope, whatever it is. So this is my slope, and this is my y-intercept. So if I write my equation out, I'm going to define my variables. X was the number of Mentos dropped. Y is the cups of Diet Coke expelled. And then I write my equation based on this information. So y hat equals the y-intercept plus the slope times x. B says to interpret the slope of the least square regression line. So we're saying for each additional Mento dropped in the bottle, the amount of soda expelled is predicted to increase by approximately 0.071 cups. So another part of the output that you recognize is where it says r squared. That is r squared, exactly as it is. Notice it's already in a percent for you. Now S right here is the standard error of the residuals. Okay? That's the standard error of residuals. Okay, so there's r squared, and I'm going to use that to find my correlation. Now, I know that it has a positive slope right here. So that tells me that the r value is positive. So to find the actual r, I have to take the square root of r squared. So I need to convert that 60.2% back to a decimal and take the square root, and I get 0.776. Now, is the linear model appropriate for this data? And explain it. Well, the only way to know if the linear model is appropriate is to look at the residual plot. Now here's our residual plot, and we're looking for any leftover patterns. There's really not a pattern here. I know you want to say that these are like sticks, but they're really not. It's not a pattern, okay? Pattern would be a curvature of some kind. So to explain this, I would say because there's no leftover pattern in the residuals, the linear model is appropriate for this data. Part E. Would you be willing to use this linear model to predict the amount of Diet Coke expelled when 10 Mentos are used? And explain your answer. Well, you got to go back to the original set of data. Look at your scatter plot. They put 2, 3, 4, or 5 Mentos in there. They didn't do anything more than 5 Mentos. So can we use this line to predict what happens when 10 Mentos are? Hopefully you know that no, you cannot, okay? Because we don't know if the linear model continues beyond 5 Mentos. This would be extrapolation. We cannot put in 10 into that equation. F says to calculate and interpret the residuals for the bottle of Diet Coke that had 2 Mentos and lost 1.25 cups. So to calculate my residual, I need to know my equation. So here's my equation that we just had. Now I'm going to plug in a 2 because 2 is my x value, and here's the actual y value. We're going to find out what the predicted y value would be. So I plug in my 2, and I get 1.14374. Now to find my residual, I'm going to take the actual minus the predicted, and I get this value, 0.10626. So when I interpret this, I would say a bottle with 2 Mentos dropped into it had about 0.11 more cups of soda expelled than we expected. Okay, I can say more cups because it's positive. So I'm going to interpret the r squared value and the s value. So remember, r squared is right there. It's pretty obvious in the table. S is right there. So interpreting is the key thing here. So let's do s first. Okay, it's 0.067. And what does that mean? It means we will typically be off by about 0.067 cups when using the regression line to predict the amount of soda expelled from the numbers of Mentos dropped. That's S. How far off is our prediction line typically going to be with context? Now r squared is 60.2%. They gave that to us in the table, so we just need to interpret. So we would say about 60.2% of the variability of the amount of soda expelled is accounted for by the regression line relating soda expelled to the number of Mentos. H says, if the amount expelled was measured in ounces instead of cups, how would the values of r squared and s be affected? Well, hopefully you know, 1 cup is 8 ounces, so we have to convert. We'd have to multiply by 8 to get to ounces, right? But let's think about it. R is based off of, or r squared is based off of r, which r has no units. Okay, it's not measured in units at all. And then s is a standard error, right? So s will be multiplied by 8 because s is measured in units of the response variable. So we would take our standard error of the residuals, multiply by 8, and it would become 0.536. So r wouldn't change, but s does. Okay, so now I want to talk about regression from the mean. And how can you calculate the equation of the least square regression line using summary statistics? That's what this is getting at. If you have summary statistics, you can find the regression line using the formulas on your chart. And your formulas on your chart look like this. Now, here's your basic regression line. And then this line right here is the same equation, but notice it's y bar and x bar. That's the average of your y values, the average of your x values. So knowing that the mean of the x's and the mean of the y is a valid point on the line, you can algebraically rearrange this to solve for a, right? To find the y-intercept, if you know the mean of the x and the mean of the y. And b, the slope. Now how do you know b? Well, b is found by taking r, the correlation coefficient, multiplied by the ratio of the standard deviation of the y's divided by standard deviation of x. So they would have to give you these values for this to be workable. So let's try one of these. Here's your equations. So write the least square regression line for the given summary statistics and show your work. So here we go. We have x bar, y bar, s of x, and y, s of y, as well as the r value. So plugging these numbers into our equations is all we have to do. So to find b, that's the most easiest one, you just take the r value and you multiply it by this ratio of s of y over s of x, and I get a slope of negative 1.12. I need this value then to solve for a. So for a, all I've done is rearrange this equation. I've just subtracted the b x bar from both sides. So I have y bar is 81.2 minus b, which we just found, times x bar, which they gave us. And that gives us an a value. Now we know what a and b are in our equation, and we can plug them in as such. Now this one has no context, so we can just leave it as x and y. From a random sample of 15 high school students, we investigated the relationship between foot length and height. The mean and standard deviation of the foot lengths are x bar is 24.76 centimeters and 2.71 centimeters. Mean and standard deviation of the heights are y bar equals 171.43 and 10.69. The correlation between the foot length and the height is a positive 0.697. Write the least square regression line to model this relationship. Okay, so they've given us the summary statistics, and we're going to use those formulas on our chart. Here they are. So first thing I do is find b. Because I know r, I know s of y and s of x. So I plug in the values they gave me, and I get a b value, a slope of 2.75. Now I'm going to use that value in the second equation to solve for a. So I have y bar, 171, minus my slope times my x bar equals this. Now I have b, now I have a, now I can write my equation. So height, hat, because that's the predicted thing we're looking for, is 103.34 plus 2.75 in foot length. So what happens to the predicted value of y for each increase of 1 standard deviation in x? Well, since the standard deviation of x is in the denominator of my slope, if this is getting bigger, then my slope is getting smaller. Therefore, if my slope is getting smaller, then that means the predicted values will also get smaller.